My name is Ali Alemi. I'm honored to be joined with a great colleague of mine, Shubham Rakshit, today. And we are here today with you to talk about low latency change data capture, or CDC, from transactional sources to data lake using Apache Flink and Apache Paimon. So we are very excited to be here at this event today because we work with a lot of customers, and we both, as you may know, are from Amazon Web Services or AWS. We are senior streaming architects at AWS. And as part of our day-to-day job, we work with a lot of customers of ours who need help, who need some guidance in terms of building and optimizing their data processing pipelines, and we help them sometimes moving from the batch processing to stream processing, and sometimes optimizing the existing data streaming data processing, and we see a lot of challenges. We work with them on solutions that will solve their problems and let them achieve the business outcome they're trying to achieve, and we are here today to share some of the learnings that we have in terms of CDC use cases, from sources to data lakes, mostly for real-time analytics, to share those with you, and hopefully you can walk away with some of those learnings. And also specifically you learn about Apache Paimon, Apache Flink, where do they fit, and when to choose them, when to use them, when we want to build similar pipelines. So we're going to talk about CDC. What is CDC? Just the foundation. And then we are going to talk about some challenges building CDC pipelines. And then we are going to introduce Apache Flink as a framework for stream processing, and also Apache Paimon and how these two work together. We're also going to talk about how Apache Paimon is going to solve some of the traditional problems with Apache Flink. So before we begin, let's first understand how data lake is relevant to the customers, and why customers build data lakes, and why data lake is important for customers. So data lake basically will give you virtually unlimited storage that you need to store, formatted, unformatted, structured, unstructured data, virtually unlimited, space for it to store it. And then you can plug in many engines, open source engines, different engines, and bring, any engine that works with the data lake for various use cases, for analytics, for machine learning, for querying, ad hoc querying, exploration, and other things. By this architecture, customers get a decoupling from the compute from the storage. And basically, they just pay for the compute with the amount of compute they need, and then pay for the storage, relatively cost-effective storage, to, for example, something like EBS, block storage on AWS, for storing that data. But in order to get the data to data lake, you will need to set up a pipeline. And that pipeline usually looks like this. If someone wants to build this pipeline in a streaming, basically with the blocks of data streaming, first, they need a process known as CDC ingestion that can first play the snapshot of the data, and then after that only captures the data changes and play those data changes in form of events into some type of a message queue or a streaming storage. And then once the data is in the streaming storage, then they will have one or more than one data streaming consumers or data stream processing jobs that they do enhancements and deduplication and enrichment and curation of that data and aggregation sometimes before to write that data lake to become available for downstream consumers. So if someone wants to build such a pipeline, with custom code, in-house tools, developing in-house tools, write some code and build some, pipeline like that, there are various challenges that they run into. First of all, the data volume can just grows so much. Once you basically build the first pipeline, you will see that now you can ingest more and more data. With the more sources that you ingest from it, the more data coming in, it becomes very difficult to maintain that code and to maintain and build that code, to design the code the way that it can scale to the volume of data you're ingesting. Also, with that complexity of it increases, there are problems with keeping the data quality, maintaining the data quality, making sure that data is, with high quality. You deduplicate correctly. You basically play the events in the right order, so you don't end up, updating a record with the wrong version. And then you also need to make sure that, you do it in a way that the pipeline is resilient, and when the failures happen, the data consistency is not going to face any challenges. Also, you need to ensure the data security, reliability, and compliance of the pipeline as well. So That's why many of customers use Apache Flink for the processes that I shown earlier. So they use Apache Flink because it's an open source, and basically the community is supporting Apache Flink, and it's very popular open source framework that that also can help you with CDC ingestion as well. So it's not only a framework that you can do a stream processing, as a downstream processor, but also can use it for ingesting data from the sources like MySQL, Postgres, and SQL Server as well, which is great because then you can just maintain one code base, right? So it's a framework that you can get started very quickly, and you can build your first streaming job very quickly by just following the getting started, documentation. And then once you do that, then you can also use the same tool for ingesting data from sources as well. So that is great by its own. And moreover, it also provides tools to ensure the data consistency and tools that you need in order to do the data deduplication, and also making sure that that your pipeline is fault tolerant. If a underlying hardware fails, if something happens and it recovers, it basically has built-in mechanism in order to process the data correctly and produce the right output that does not impact your downstream applications. It also has integration to many sources and targets. So that's another advantage. So you can basically deliver that data to many different targets that you may have. The most popular one, like a data lake or, data warehouses and other solutions. Also, one thing that I want to highlight here is that it provides a data abstract or a data structure as an abstract called dynamic table that you can basically, with one structure, work with both unbounded and bounded data and work with the data streaming event as if they were a record in a table. So that basically is a very nice abstraction that makes it so simple for everybody to just understand the data, work with that data. So we'll talk more about that. But again, with using Apache Flink for CDC, there are still other challenges. Let's first focus on the challenges that comes with the first part, when we are basically ingesting the CDC data and basically sending it to a stream storage. So one of the most popular streaming storages, that is out there and work, really well with Apache Flink is Apache Kafka. So we are seeing that Apache Kafka and Apache Flink almost basically work together in any solution. And Apache Kafka is like, the de facto standard for streaming storage for a message queue, that you want to basically have a storage that is optimized to store the record in the same order that they are produced, and then basically keeping it that way so then the downstream consumer can process the events in the same order. When you want to build a pipeline like that, you obviously get some pros from the Kafka ecosystem and Flink ecosystem together, which is low latency, and then you can also horizontally scale this solution to the volume of the data. But there are challenges with that. As you can see on the left side, my code looks like this. First, I need to create a table that points to my source, and then in that table, I need to explicitly define, the columns or the attributes of the data. And same I need to do for my target. And then I need to basically write a query that basically submits the job to a Flink cluster to ingest the CDC and write it to that storage. So anytime that a new column, a new attribute has been added, I need to come here, update the code, and restart the job. And then there are also other challenges that is inherent with Kafka architecture. We're going to talk about that a little bit here. So with CDC, what we are seeing is that there are various use cases that you would need to replay the data, known as backfill. Either the downstream consumer finds the data quality issues or have failures or need to restart from the clean slate, and they will ask you to replay all that data for them. So when that happens, you have two choices with Kafka. Either you need to keep all the data in Kafka, which basically causes that as you add more and more of these jobs, you end up running out of space, and then you will need to keep adding storage to your Kafka, resulting your Apache Kafka grows bigger and bigger, which associated with higher cost. Or you say, okay, no, I will delete the data from Kafka, only retain maybe 8 hours of the data. But then anytime anybody wants to replay the data, we'll go to the source and then we'll replay the data from the source. That also is problematic too, because what causes is a huge spike in the storage utilization of Apache Kafka. And then for a short amount of time, you will need to scale the storage. And then once the data is deleted, then you need to scale back in it. That is not a trivial operation for the Kafka administrators. So we just said that data lake can provide us with a very cost-effective storage solution. Why not we use data lake instead of Kafka for our streaming storage? And let's think about that. So Apache Flink has a sync connector to a data lake. Okay, so we can use it in order to, instead of writing to Kafka, we can write it to basically maybe if you are working on AWS, we can write it to an S3 bucket. And then the code doesn't need to change that much. We can pretty much reuse the same code that we used to have. So the pros we get is we have access to scalable, virtually unlimited storage, so we can retain all the data there. And then downstream consumers are welcome to replay that data as much as they want. It reduces our cost. We can do infinite retention. What are the challenges we are introducing to the system? Well, data lakes are not designed for low latency, so we're going to experience some higher latency, but maybe that is okay for some use cases. Let's talk about other challenges. What we are going to do with dealing with data duplication? What about the order of the events? Can we guarantee that the records that we write to S3 are going to be replayed the same order that we wrote them? Probably not. And still we have the outstanding challenge of a schema evolution. We haven't solved that one yet. So let's see how we can solve any of these challenges. If we can solve these challenges, basically we're good, right? Because we solved the other challenges as well. So here's where open table format engine is going to help us. There are open table format engines that help you to manage a very large data lake, in cloud vendors, or if you're running it somewhere else. The popular ones are Apache Paimon, Apache Hudi, and Apache Iceberg. They basically sit in between your compute engine and the file format that you're using, and they basically do some data lake management for you. And we're going to talk about how is that relevant to the challenges we are trying to solve, how we can use them to solve our challenges. Before we do that, let's see how the code looks like. So in Apache Hudi, if you're using Apache Hudi and you want to write a CDC data, and we want to make sure we do the deduplication as well in that process. So the job, basically, the code is, after we define the source and target, here's the basically the line of command that will build the job and submit to the cluster. Here's that code looks like. We insert to our target table, selecting from source table. Same is for Apache Paimon. For Apache Iceberg, we need to explicitly enable upsert, which means if you find a record with the same value in defined, unique identifier, then overwrite that record with the new version. So that's how we can do the deduplication. So just so you know, in the concept of CDC and upsert, here's how these three frameworks differ. But let's now talk a little bit more. What is Apache Paimon? And let's do a quick introduction of Apache Paimon. So Apache Paimon is basically, you can imagine it as a best buddy of Apache Flink, a very good companion for Apache Flink that will provide us with, benefits that is super relevant to stream processing. The first benefit that Apache Paimon provides is with a single framework, we would be able to satisfy two write patterns. One is the append only, similar to Kafka logs that you just keep appending events at the end of the partition or the topic. You can do the same with Apache Paimon. So you can basically keep appending the data in the same order that the event appears or produced in an Apache Paimon table. And then also at the same time, you can basically do a lookup key value lookup, which is relevant to CDC data. So with one framework, with one abstract, you would be able to basically deal with two types of data that you might have, the data that is append only and the data that is CDC. So it satisfies both use cases with one table. That is really great. Another thing is it also is a framework, is a basically open table format engine that you can use for analytic use cases, for ad hoc querying, running ad hoc analytic queries as well. So Apache Paimon supports file systems like Hadoop and S3 and other cloud vendors' storages, and also aside from Flink, it also works with other popular compute engines such as the Spark, Hive, Trino, Iceberg. And also in terms of Iceberg, I need to mention that it basically provides an Iceberg compatible reader. So if you are using Iceberg somewhere else and you want your compute engine to interact with the Paimon table without you needing to swap the source connector and basically feed it with another connector to read that data differently, you can use this Iceberg reader Paimon capability in order to use one compute engine to read both from both Paimon and Iceberg within one basically Iceberg compatible protocol. All right, so we are now going to talk about the schema challenges. I would like to hand it over to Shubham, who's going to dive a little bit deeper and take us through how we are going to solve schema evolution. Thank you.
Okay, so first of all, good morning, good afternoon, good evening to everyone who's joining the session, depending on from which region you are joining. My name is Shubham Rakshit, and I'm a streaming solution architect in AWS. And let's continue the discussion about the schema evolution. So when we talk about the schema evolution, it's important to understand that how the schemas evolve and when you are actually syncing the data from the source database to a Paimon table, right? Think about that. If you are doing it in normal data lake, we are expecting that when you add a particular column in the source database, the schema should also be the same field should also be added to the Paimon table or to the data lake itself. Now with Paimon table, we have got something called the Paimon table actions, which can literally actually take the schema directly from the source data tables and put it into the Paimon tables directly. It can do a direct synchronization. It can do a database synchronization, table synchronization from MySQL, Kafka, Pulsar, and MongoDB. It also supports any forms of other table and database. And it's like a Flink job, a separate job that you are running in the Paimon action as a jar file. And that particular job will read the data from the MySQL database and write it to this particular Paimon table. So basically, it's a one Flink job that helps you to actually run and sync all the schemas. And tables get automatically created and synced automatically. And it also supports the upserts for the primary key. If you are actually making any updates in your tables in the source table, that same updates also be reflected in the Paimon table. With that, let's talk about the CDC part, right? So when you're doing a CDC, we are writing small files. We are rewriting them due to updates, and then we need to read those data from the lakehouse. Let's take an example. Say that we have an orders table, and that orders table, we have got the orders data, and one of the field over there is the creation date. And we are using a Paimon action jar, and then basically it will copy all the data from the orders table and write it to the Paimon table. Now, definitely, since we have a creation date as one of the field in the orders table, the partitions are created based on the creation date. So some partitions will, when you are syncing the data, some partitions will have more data compared to the other partitions. So that means we'll end up having small files in multiple different partitions. And therefore, it will end up having multiple smaller files, and we need to actually do certain things to the smaller files because it can also have an impact in terms of the read performance. Now, before we understand how we can deal with the small file issues, let's understand the Paimon file layout. It starts with a snapshot. A snapshot file is written in a snapshot directory and is suffixed with a increasing integer. Okay, a snapshot file contains the information of the schema that is in use and links to the manifest list. And the manifest list points to the manifest file, and that points to the data file. Well, we are not going to talk too much about the manifest list and manifest file in this particular session. I recommend you to go and check the Paimon documentation to actually learn more about it. I'm going to focus a bit more about the partitions and where the data has been written to. So the data files are organized into one or more partitions, and each of these partitions can further subdivide it into one or more buckets. Currently, Paimon supports ORC format, Parquet format, and Avro format as the different data file formats. Now, within each partition, the data is distributed over the buckets according to the bucket key, or if the bucket key is not present, then using the primary key. And the data within the files, they are ordered based on the primary key. When you write the data to the partition, the data is routed in the specific bucket based on the bucket key or the primary key. And each bucket is organized into a log structure merge tree. Partitions and buckets solve two different purposes. Okay, Partitions allows for more efficient queries by allowing the compute engines to more effectively prune the data files when you are reading the data, whereas buckets actually help you to add more parallelism to read and write. Now, when you are writing the data to the log structure merge tree, a log structure merge tree has got different levels, level 0, 1, and so on. When you're writing the data, you always write data into the level 0. Okay, so in level 0, you can end up having multiple sorted runs. Whenever you are writing it, every time you're creating a sorted run, which is composed of multiple data files. Now, although you'll end up having multiple sorted runs, the beauty of sorted run is that the data itself is sorted within the data file. That means it helps in efficient binary search, leading to very fast read operations. Now that the data has been written to the level 0 and it ends up having multiple sorted runs, we need to actually merge several sorted runs to build one big sorted run. And this procedure is called compaction. A single bucket has got a writer thread that is writing to level 0 and another compactor job that basically running in a separate thread. Okay, and writers always write to level 0. However, the compactor, they read data from the level 0, merge this data file, and write it to the higher levels. As this writer and the compactor, they both work on different levels, they do not conflict with each other. And this compaction process ensures that the small files are compacted to large files, which becomes more efficient from a read perspective. So let's compare how this compaction looks like compared to other open table formats. By default, compaction in Paimon is asynchronous in nature. So when writing the data, occasionally, asynchronously, it will actually do the compaction of the files. So we call it same job compaction. And however, if you have multiple writers writing to the buckets, you will require a dedicated compaction job that is doing the compaction in the Paimon. Hudi also supports same job compaction and a dedicated compaction job. However, Iceberg only supports a dedicated compaction job via a table maintenance operation, whereas it doesn't support any same job compaction. Now that we are writing data to the Paimon table, we need to actually read this data from the Paimon table in a streaming manner. So we have replaced our Kafka with a data lake, which is the Paimon table. And then our Flink job, the downstream processor, basically needs to read data from this Paimon table, and then you need to send data to some target destination. Here, the target is another Paimon table. So we are now concerned about how this Flink job or the downstream processors are going to process the data from the Paimon table in the data lake. So from a code perspective, it's not much of a change in the structure, how it looks like. You still need to create a create table for your source. You still need to create a target table and then select the data from the source table and write it to the target table. However, using Flink, we can actually do a streaming read from the Paimon table, and it also supports reading from a specific consumer offset and configure a consumer ID. Let's look at that. So a consumer ID is used to record a consumer offset in a Paimon table. Let's say you have a Flink job and you need to kind of modify the compute logic of the Flink job. And once you have modified the compute logic, your deployment topology of the Flink job has changed. So you are not able to actually retrieve the consumer offset from the Flink state. Now, if you use a consumer ID, it stores the corresponding consumer offset in the metadata files of the Paimon table. This way, a consumer can resume from the previous offset, even if the deployment is restarted in a stateless manner. Now, often the snapshot files are expired, right? And then it gets deleted. If the snapshot files are deleted before it is consumed, then an error can happen. With consumer ID, it will prevent the deletion of an expired snapshot that are not consumed. This consumer ID is a very unique concept in Paimon, and it's very closer to how Kafka also operates. So if you're working on Kafka, you can find some kind of similarity in how the consumer ID behaves in Paimon. You can also read data from a specific consumer offset. You can say that I want to read the latest data, and in doing so, it will only consume the incremental data after the deployment of the job. Also, you can read data from a specific timestamp from where it will read data from a specific point in time. Now, if you have worked on a data pipeline, I'm sure that data backfill is one of the challenges that you have faced, and you have been considering that how you can actually make your life better in terms of the backfill. And there are certain use cases where backfill is important. For example, you need to make some kind of historical data correction, some kind of changes in the data that it needs to be done in the past, and you need to actually reprocess the data again. Or maybe your Flink job or your downstream processing job needs to have a change in logic. That means you need to reprocess the data. Or it could be something like you want to restore your downstream table to a specific point in time, or even the Flink state to a specific point in time. The whole idea is that using Paimon, you do not actually need to go back to your source database actually, because you've already written the data to the initial raw layer of the Paimon table. All you need is to reprocess the data from this initial layer of the Paimon table, and you can populate it. Now, basically, if you need to kind of repoint your data to a specific point in time, there are various ways you can think of. One of the things that happens is that in Paimon is that Paimon has caused snapshots, and it provides an easy way to query historical data. But in most scenarios, a job will create too many snapshots, and the table will expire the old snapshots according to some table configuration. Now, if your snapshot will expire, you won't be able to query it. To solve this problem, you can actually create a tag based on a snapshot. And the tag will actually maintain the manifest and the data files of the snapshot. A typical usage is like you can create a daily tags, and then you can actually say that you can go back to a specific historical point in time for a specific day and read data from that point in time. Now, let's compare these read patterns and how it actually compares with other open table formats. With Hudi, see that you can do a reading of the data from a specific start and end commit time or from the earliest. With Iceberg, you can actually consume the data from a specific snapshot ID or a tag or a branch. Paimon here provides broadest possible option. You can read data from a timestamp, from a snapshot ID, you can consume from a tag, from a branch, or even configure a consumer ID that will map to a specific consumer offset. Now, what can a robust merge engine do? Paimon, by default, is merge on read. This means a reader must merge a result across multiple sorted runs, and that each primary key of the input data only has one row in the output data. By default, Paimon supports the merge engine duplicate merge engine, which ensures that the query only return one row per primary key. So the data is merged based on the sequence number order and producing one row per key output. So here in this example, I have got two records, one Alex A and one Alex B. One Alex B has got a higher sequence number than one Alex B. So using a duplicate merge engine, it will pick up the one with the highest sequence number, that is one Alex B. Also, there are other merge engines type. For example, a partial update merge engine, where the users have the ability to update columns of a record through multiple updates until the record is complete. So here in this example, I get the first record as one Alex, and there's no email with it, with the first record. With the second one, I do not get the name, but I get the email, which is then what happens is that with partial update merge engine, the same record is updated and the record is made complete. Paimon also supports other different merge engine types like aggregation, first row, and so on. And it helps you to simplify your Flink jobs. And using a partial update merge engine, you can think of like reducing any requirement of creating stream-to-stream join, and it can effectively reduce your Flink state size. So before we had Apache Paimon, we had an architecture like this. We had the tables, the product and discount, which are which you are doing a CDC from those tables into the Kafka topics. And we have a Flink job that is reading the product table, product topic, and doing a key by operation using the product ID. And then it actually joins with the discount data and figures out the discount that's applied on the product. With this particular architecture, we have challenges with the schema evolution, how the Kafka storage can scale, how also like what would be the capacity during the backfill. You have a longer retention of the data within the Kafka itself. And of course, since you're doing a streaming join, the data is holding the state, so you require a larger state, and this can lead to a higher cost. With Paimon, once you move to Paimon, now we can actually do a simple DB synchronization from the database to the Paimon tables, and we get the product and discount Paimon tables. And we can write a Flink job that's reading data from the product table and the Paimon table, do a lookup join, and check for this respective discount item for the particular product, and can figure out the discount applied on the product. Here we have a full support for schema evolution. Our Kafka is now replaced with the Paimon over here, just based on a scalable storage like S3. We have got infinite retention, backfill becomes much easier, and your Flink state can also be reduced leveraging a lookup join with the Paimon table. However, whenever doing a lookup join, you need to be careful about whether your use case is a good candidate for a lookup join, depending on what volume of data you are dealing with it. And this can lead to a very low cost. So now we're coming to the end of this presentation. So let's kind of recapitulate what you have learned. We learned about how data lake can solve the storage-related challenges with the latency trade-off. Kafka will always have its value. It is still recommended if you are building a low latency pipeline, go for Kafka. But if you have a kind of a ability to have a little bit higher latency trade-off, and you can have a minute level latency or so, you can use Paimon on top of S3. You can use Paimon actions to synchronize the database to the data lake directly, and rather than relying on the Flink state, you can now scale using your Paimon tables. And if you are concerned about the tooling, that whether you can use your favorite, readers compatible with Iceberg formats, so you can read with Paimon. Paimon as now supports the Iceberg compatibility. That means it generates the metadata files which are Iceberg compatible. You can use your readers that are Iceberg supported readers to read the data from the Paimon table. Additionally, Paimon supports other rich margin genes like aggregate margin gene, first row, or so on. And I recommend you to have a look into the documentation or read more about it. And there's also another feature of Paimon that makes it behave like a Kafka for append-only table. But that would be another session for another day. So with that, we come to an end. Thank you very much. Thanks for staying by, and I hope you enjoy the session.